Hello, I'm Christina and I'm the team leader of CTU Robotics, and this is our main project, Rover PERUN Gen 3. Our multidisciplinary student team from Czech Technical University in Prague consists of more than 50 members, mainly from the Faculty of Mechanical Engineering and the Faculty of Electrical Engineering. Our team works in 5 departments that can be listed as Mechanical, Autonomous, Electrical, Science, and Marketing. Mechanical department is tasked with the development of modular robust chassis and reliable mobility system. From there, the electrical department takes over and ensures that all the systems on board communicate, power up, and work together efficiently. Autonomous department uses this network to utilize computer vision on their objective of autonomous manipulation and navigation. The science department deals with space geology and samples analysis. Marketing department represents our team on events and on the internet in a cooperation with our socials group that takes care of creating content and promotion of our team. We also have a dedicated group for the development of the drone. We want to participate in the ERC 2026 to test ourselves, inspire future generations, represent our university, and witness different engineering approaches.
The mobility system of Rover is based on rocket kinematics, with a wheelbase of 850 mm and low center of gravity localized under the main frame. Rover maintains excellent stability in rough terrain. These design choices allow the rover to climb and traverse through slopes exceeding 40 degrees and navigate various obstacles with ease. The entire chassis is fully modular, ensuring that repairs are simple and remarkably fast in case of failure. Our primary focus was on weight reduction. By optimizing the use of lightweight materials such as carbon fiber, aluminum, and 3D printed parts from PETG or PC blend carbon fiber, we successfully reduced the rover's total weight by over 25 kilos compared to the previous generation. A unique feature of our wheel design is integrated grounding system, which protects all onboard electronics from static electricity. All electronics are housed within a sealed frame constructed from aluminum profiles. The frame has several mounting points for additional systems, such as the robotic arm, drilling tool, or cam tower. For the internal layout, we implemented a newly designed modular system to secure all electronics.
Every subsystem in our rover depends on reliable power and data. At the heart of the power system sits a custom assembled battery pack built from high-density lithium-ion cells. At 12 amp-hours and around 40 volts nominal, we get approximately 500 watt-hours of continuous energy. A commercial BMS handles cell balancing, thermal protection, over current protection, and much more, so we never push the cells over their working limit. Power distribution is managed by our custom-designed PSU PCB. It includes step-down converters for sensitive electronics, switchable outputs for power routing, and real-time current monitoring at every branch. The PSU directly interfaces the emergency stop button, which instantly cuts power to all motors. For locomotion, we use BLDC motors with integrated drivers and planetary gearboxes. They communicate over a high-speed CAN bus. For low-level sensor integration, we use microcontrollers with network connectivity, so there is no need for additional USB or serial bridges. Our primary data link is a Wi-Fi access point. If that degrades, we switch over to LoRa for critical telemetry. For real-time manual control, we use a dedicated FPV feed, prioritizing latency over quality.
Our compute is split across 3 machines. 2 Raspberry Pi boards handle motor control for the base and the arm, while onboard computer with Intel processor and 32 GB of RAM handles SLAM, data fusion, and mission logic. For perception, we rely on LiDAR units paired with RGBD cameras, providing us with great understanding of robot surroundings. Localization is built around fusing wheel odometry, visual odometry, and inertial data through 2-level Kanban filter. First layer keeps short-term pulse smooth, while the other anchors us globally through our landmarks. On top of that, AirTap map puts a consistent 3D map with a loop closure, correcting any accumulated error. Nest2 stack then plans global path through the waypoints and replans local trajectories, avoiding any rocks, dynamic obstacles, and other rovers. For managing all subsystems, Rover relies on onboard decision-making, powered by behavior tree with built-in failure handling. Our drone development crew closely cooperated with another great CTU group called Multi-Robot Systems. Together we have developed our very own drone called Jarilo. It is built on a lightweight modular carbon fiber frame featuring a battery IMU vibration dampening system engineered for maximum stability in the field. Its brain is a Raspberry Pi running ROS 2 inside Docker, enabling fully independent onboard computing and fully autonomous operations. Its eyes and ears are onboard cameras fused with an IMU through visual odometry, enabling all-scenario GNSS denied navigation both indoor and outdoor. And when GPS is available, Jarilo seamlessly integrates it for even greater positional accuracy. For mission control, we use MATLAB Mission Controller for image processing and high-level decision-making. Jarilo also features geofencing capability, allowing operators to designate a precise area of operation and ensuring the drone stays exactly where it needs to be. The drone operator can monitor operations through an RVIS panel, and a backup manual control is available via a radio controller. With safety being our top priority, the drone features an emergency Autoland function activated by fail-safe conditions such as signal loss or critical errors, ensuring safe returns in all situations.
Our manipulator is a robotic arm with 6 degrees of freedom. We use map motors with rotary encoders in every joint. We have a set of end effectors that we can switch between, for example, basic gripper or a digger. There will be a camera mounted on the gripper, which we can use to get image data or a point cloud. We can further use that for autonomous behavior or planning trajectories with collisions. The arm has its own detached Raspberry Pi, separated from the main rover, which runs ROS 2 and MoveIt 2 for planning the trajectories, and it also runs a servo node for manual operation. Our drilling system has been designed as a two-level movable console. First, the outer structure reaches the ground, and then the drill bit is engaged. A plexiglass tube encloses the drill bit, and the lid closes the tube as soon as it exits the soil fully. The system's capacity is 300 grams of soil at a drilling depth of 30 centimeters. After successful drilling, the soil is deposited in a sealed container capable of measuring weight.
The science tasks focuses on investigating the regional geological diversity and the processes that formed it, with particular interest in the regions of Dow Valleys and the Eastern Hellas Basin. These terrains provide evidence of volcanic activity, sedimentary transportation, and possible ice-related modification, making them valuable targets for surface exploration. To address these challenges, we designed a scientific platform capable of combining large-area geological observations with direct surface and subsurface analysis. The rover's optical systems provide both navigation support and scientific observation. Wide area imaging allows us to identify geological contexts, surface textures, erosional patterns, sedimentary structures, and morphological features associated with past geological activity. These observations are then relayed for further analysis and interpretation. Working alongside the optical systems, our sampling and drilling mechanism allows us to reach samples from beneath the weathered surface layer, reaching depths of up to 30 centimeters. Collected samples are transferred into sealable analytical containers, designed not only for transportation but also for onboard experimentation. Within the rover science package, the samples undergo a detailed physical analysis, including measurements of mass, texture, grain characteristics, and structural appearance via close-range imaging systems. Through the integration of mobility, imaging, sampling, and in-situ analysis, we aim to gather a better picture of the current environment and the processes that helped shape it in the past.